Hi, welcome to this presentation. My name is Heuschkel, and I am an anthropologist working at the Applied University, Mittweida. The project I'm going to present is about the potential of digitization and digitalization for work with human remains in anthropology and at cultural heritage institutions. There are several people and institutions cooperating on this project, so the first thing I'd like to do is to introduce them all and to also tell a bit about the genesis of the project. Our project team is composed of anthropologists, IT specialists, and archaeologists. Most of us work at the University of Applied Sciences in Mittweida, which is located in the middle of Saxony in Germany. There, we are part of a forensic science investigation lab. That's a research group that specializes in digitalization within forensic science. This includes research on digitization strategies such as 3D modeling. Since 2017, the group has been extending its focus to anthropology and human skeletal remains, also addressing possibilities of digitalization in this field. To this end, it's cooperating with partners throughout Germany. This project was developed in close cooperation with the University of Göttingen. Its Department of Historical Anthropology and Human Ecology has got a long tradition in anthropology, and moreover, an extensive collection of human skeletal remains. Also a partner in this project is the Archaeological Heritage Office of Saxony, as a cultural heritage institution that deals with human remains. The project's starting point is the Rödelheim skeletal collection consisting of more than 200 skeletal remains of former soldiers that were part of Napoleon's army. It's a scientifically valuable collection that is still being researched by anthropologists at the University of Göttingen. However, the remains are to be reburied in 2021. Faced with the untimely loss of the material, digitization as a way for preservation soon came up and paved the way for the project. Within the project, the University of Göttingen provides the skeletal material that is to be digitized as well as professional expertise. While the research group at the Applied University Mittweida is responsible for the development of the project's digitalization processes. Tests for evaluation are carried out jointly. As a potential user of a proposed solution, the Archaeological Heritage Office of Saxony makes a further important contribution to the evaluation of the project results. Called AnthroWorks 3D, and moreover, use it as an example to address the benefits of digital transformation processes in this context. Before we dive into all that, let's have a look at what human remains are all about and why that digitization would be worthwhile. If not forensically relevant, human skeletal remains usually occur in association with the discovery and subsequent excavation of burials and burial grounds. Thus, in the case of Saxony, the Archaeological Heritage Office is responsible for the recovery and subsequent care. But why not just rebury them? Human skeletons are carriers of information that anthropologists gain access to by reading the traces on the skeleton, for instance, through the examination of differences in the morphology of the bones. For this purpose, they apply methods of measurement and make visual assessments, describing and categorizing visible and often palpable characteristics. From the data collected in this way, it is possible to derive biological attributes such as sex, age, height, and health. The assessment of one skeleton provides a biological profile and clues to the existence of the individual. When the remains of groups of individuals are examined, the accumulated information may give insight into their demography, events, or circumstances at the time, ranging from their ethnic affiliation, cultural behaviors, up to their living conditions. The analysis of human remains thus helps reconstructing and understanding the past. This makes them part of cultural heritage. However, there are several challenges that may compromise the gain of information. Difficulties in the documentation and data recording of the remains are one of them. Due to human variability and the many influences that can act on bone, there is an abundance of obtainable data. but this data is hard to describe in a manner that is objective and comprehensive, as well as flexible yet consistent. Existing data recording systems are individualized rather than standardized. A solution that can be universally applied is still missing. Consequently, there are issues of compatibility and thus comparability. The use of skeletal collections for reference or research is essential for anthropological analyses. However, access is oftentimes only possible on site and therefore confined to a small number of mostly local researchers. This means that where there is skeletal material, there is usually a shortage of anthropologists and vice versa. From the moment of excavation, bone is subject to constant gradual deterioration due to transport, storage, or handling. With increasing wear and tear of the skeletal material, its value as a source of information decreases as the traces on the skeleton vanish or become distorted. Indeed, the availability of human skeletal remains is not guaranteed, and it is possible that they may become subject to repatriation claims or have to be reburied, as was the case in this project. Against this backdrop, current digitalization and information technologies, as used in video game development, could be a powerful tool for anthropology to tackle these challenges. Since they have so far been applied in only a few scientific fields, the development of the tool AnthroWorks 3D was an opportunity to test methods and knowledge of video game development for their use in the work with human skeletal remains. Hence, our objective was to make use of such methods to digitally preserve the material in a sustainable way that captures as much information as possible and to facilitate the utilization of the digital material. For this purpose, the aim was twofold. First, to develop a practicable procedure for the digitization of skeletal material, leading to true-to-life, high-resolution 3D models. As a sustainable means of preservation, this is supposed to go beyond mere visualization. Therefore, the second aim was to develop an easily understandable real-time application, which enables the annotation and analysis of these models using typical analog anthropological methods such as measurements. Furthermore, the application was to allow for saving and sharing the models with the captured data. For these developments to be successful, it was important to ensure that problems that usually prevent digitization and digitalization from being permanently established in practice would not deter the tool from working in as many environments as possible. For that reason, the focus was also set on the early evaluation and review of the developments for all relevant aspects. These included making sure that it would require little time, money, and staff, could provide high resolution of the models, and would consider factors of user experience and usability. Now, let's see how all this turned out. First, we have a look at the procedure for the digitization of the material. The photochromatic technique structure for motion was a method of choice because it produces the required quality by relatively low-cost means that are oftentimes already available. Hence, a setup was developed to record the image sequence. It is structured as follows. The camera settings, the softboxes, and the mount were adjusted to retain the required quality of the image sequence. The mount is made of acrylic glass and anti-reflective glass, which way does not conceal any part of the bone, making the mount invisible during later processing. The skeletal elements, bone fragments included, can be placed on the mount without any special arrangement, no matter the size or shape. In addition, it enables several elements to be scanned simultaneously. Also on the mount next to the elements is a little cube, required for the subsequent scaling process. Attached to a tripod, the mount is then installed on the turntable at the center of the setup. The turntable is used to rotate the elements, and the image sequence is recorded by 3 cameras that capture the bone from a different perspective each. The models are then generated from the image sequence. This is done by using the photogrammetry software Measure. Measuring permits the whole process to be easily automated. Afterwards, the software MeshLab is employed to improve the generated models and their subsequent performance in the application. In a final step, the model was manually scaled to its desired size. Since Meshroom's October 2020 update, this can now be achieved through the use of the software's automatic scaling feature. The final model is generated from 159 images taken during a scanning round. In this image, 3D models of the bones of the whole hand are depicted, which were all scanned in one round. Since each bone constitutes a separate model, for the scanning process, it's not necessary to arrange them according to their anatomical position. On the practicability of the procedure, it can produce high-quality models while currently a scanning process takes about 6 minutes, and the total time for recording the image sequence of a whole skeleton is about 5 to 6 hours. The calculation of the models, which can be done overnight, takes about 7 hours. In terms of resources, it can be added that the software employed is entirely open source. Meanwhile, the calculation requires powerful computers with corresponding graphics performance. Also, the procedure is easy to implement and maintain as much as automized. Finally, with 12 square meters for the setup, there is only little space required. Now, let's proceed to a real-time application for the annotation and analysis of the models. It was developed using the open source and cross-platform game engine Unity. Let's go through the features one by one. First, from pan and tilt to zoom to orbit, the user can freely move around the model. In addition, there are predefined views that correspond to terms of anatomical orientation. The general view shows all imported models in a placeholder skeleton. There, it is possible to select individual or multiple elements to hide or isolate and examine them in the detail view. In that view, the models can be temporarily moved and rotated as needed. They return to their original position when one returns to the general view. The files constituting a model are imported through a form, which is additionally filled out with properties such as the anatomical term of the bone. Confirming the entry closes the form, and the files are combined to form the model in the application. The position of a model can then be adjusted using the transform tool to move and rotate the model. It can be fitted into the placeholder in the shape of a selected bone. Anatomical directional terms provide further orientation. Once the calibration is finished, the bone model is then displayed in the general view. With the transform tool, the model can be moved in the 3 depicted directions and rotated around the depicted axis. It's also possible to scale the tool. In the detail view, annotations can be added through the creation of different shapes, such as points on the models, to which it is possible to assign various information, such as the kind of characteristic, age-specific, relevant for height estimation, and so on. All entries or changes are automatically assigned to the respective author or editor and provided with a timestamp. Annotations are then displayed in a list. Further shapes include lines, and surfaces. In the list, annotations can be selected for further editing or manipulation, such as fade in and out, or focus. Distances are measured by the allocation of 2 points. Preliminary measurement results are temporarily displayed. Final measurement results are saved in the same way as annotations, whereby further information can be added. They are then listed among the other annotations where they can be selected, edited, or deleted. The tool to measure circumference consists of a disk that can be aligned to the model using the transform tool. The measurement is taken when an orb has circled the disk. This tool, too, allows preliminary measurements. Angles are measured by placing 3 points on the model. The user interface is based on existing 3D editors and contains elements such as buttons, text boxes, lists, and forms. For reasons of clarity, the features are split onto different menu bars. One for features such as import, the next to display annotations, the toolbar to switch views or adjust view settings, and finally one bar for all the tools. The model and all annotated information are saved so that when imported again, the models are placed in the corresponding position and all measurements and annotations are again placed onto the models. Initial experiments and surveys were conducted to determine from early on whether the project's approach was worthwhile and had the potential for practical application. One experiment was to compare the performance of anthropological digital examinations in the form of measurements and visual assessments on the model in the application with those obtained manually on the physical bone. Another objective was to evaluate the user experience, that is, the usability, as well as the behavior and attitudes of users in relation to the application. Potentially confounding influences such as the experience of the users in dealing with 3D viewers also needed to be considered so as to be able to exclude them. Due to the small sample size, the results are preliminary and can only be considered as trends at most. Here are some results from the surveys that show that subjects with anthropological background found the application suitable for anthropological work, albeit as a majority reported with limitations. The training period was estimated by the majority to be less than a week, and the measuring points as well as morphological features on the model could be found in either in all or in most cases. Broken down into different aspects, the preliminary trends indicate that the current procedure offers to completely digitize skeletons on a larger scale and in a feasible way in terms of required effort and equipment. The quality of the generated 3D models is sufficient for their use in anthropological work in combination with a developed application. However, until now, the quality is not enough to make a model of a skeletal element a digital twin of its physical equivalent. In terms of suitability for examination, the trend suggests that the reliability of measurements taken in the application is comparable to that of the measurements on a physical bone. However, visual assessments seem to be more difficult on the model than on the physical bone, since they vary more. Furthermore, the trends indicate good basic usability and, especially for the anthropological test subjects, overall good user experience whereby potential for improvement could also be identified. From a technical point of view, current shortcomings do not affect the underlying concept of the work and can hence be resolved through continuous development. Difficulties that have been identified rather stem from differences in the digital and analog execution of methods. In the former, judgment of perspective and depth was more difficult. However, a learning effect was noted to solve these issues with time. A hitherto unsolvable problem is that, contrary to a real bone, a digital model is impossible to palpate. Palpation, though, may contribute significantly to the overall assessment of the bone. This shows that the application cannot replace the physical examination, but it is a good complement. Still being at an early stage of development, it is methodologically sound and offers a combination of efficiency and simplicity. Consequently, it can already be applied on a small scale. According to experts, AnthroWorks 3D has the potential to contribute to digitalization processes in anthropology and in cultural heritage institutions, namely to address challenges in the work with human skeletal remains regarding issues of preservation, conservation, documentation, access, and research that have been persisting for years. For one, the information is recorded directly onto the model and can always be viewed in connection with the original source and all its unprocessed and therefore undistorted information. This makes the recorded information more comprehensible and reproducible, resulting into a more sustainable documentation. Moreover, it offers an intuitive, approachable alternative to conventional recording forms. At the same time, it supports flexibility as, for example, it allows the objective documentation of bone parts or fragments. Hence, the digital preservation helps to ensure the availability of the skeletal material in a sustainable way as it allows for further use of the models, for instance, to make preliminary assessments or to gain a first impression. That way, it indirectly contributes to the protection of the original material. This also presents a possibility for researchers to have access to the material regardless of the location or the condition of the material. This would enable comparisons of collections and studies with larger sample size. In turn, collections could be studied by a greater number of researchers. Finally, the model could be useful for teaching purposes or be a part of innovative archaeological themed exhibitions. To make this possible, future work aims for the integration into a collection management system with version control, sophisticated user management, and the possibility to include other formats such as CT scans. Further in-depth work, which will be addressed at a given time, will deal with possibilities for automatic bone recognition, automatic annotation and measurement of skeletal elements, as well as with option for more advanced analysis using artificial intelligence. In a nutshell, AnthroWorks 3D is a tool that combines a procedure to generate 3D models of skeletal material with an application to annotate and digitally analyze the models. Its underlying approach puts an emphasis on interdisciplinarity and practicability and seeks to exhaust existing know-how and technologies such as photogrammetry, video game development, and user experience research to link these with anthropological expertise. For the future, we seek to continually improve and further develop the tool. And that brings us to the end. These are our sources. We would like to thank you for your time and attention today.